I'm going to talk about work I've been doing in the Shale group. That's in collaboration with folks at BMS, and we make heavy use of Psi4. The method's called CLIF. It's a force field that uses machine learning. So why am I working on a force field? The folks at BMS are very interested in studying things that involve drugs and protein pockets, obviously. And so what we want and what they really like is running SAPT on these things. Problem is that these systems are often much too large to get high quality SAPTs, over hundreds and hundreds of atoms and so forth. And so what we really want to do is basically how can we sort of get those numbers, high level SAPT quality interaction energies for protein ligand model systems, and we want to do it many times. And that's kind of an important point. It's not just can we do a few sort of state-of-the-art calculations, but we have maybe hundreds of thousands of these things. So it has to be really, really fast. So what can we do to get that kind of speed and accuracy? Approaches that our group is interested in are to use machine learning to do this. One can also use something like force fields. And what we do here is a combination of the two. And so what CLIF does is it uses sort of a high-level force field functional form that sort of is chosen from the literature, more or less, and we parameterize it automatically with machine learning models. This idea of combining these two things is not new to us, certainly. We didn't invent it. And a lot of this work is sort of built upon this method called IPML that was introduced a few years ago by Schriber, von Lilienfeld, and a few others. So I'll just show sort of the functional form of the force field. I won't go through all the terms and all that kind of stuff, but what I will say is that there's a term for each SAPT component, and I've highlighted certain parts of each term with either blue or red. These blue things are all things we get from machine learning models, and they're all related to properties that can be computed from molecular densities. And so when you want to apply a high-level force field to a new molecule, you have to get these parameters somehow. And for advanced force fields, a lot of times what people do is just do a QM calculation to get, and then do some charge partitioning and get things like multipoles here or atomic widths. If we're applying this to hundreds of thousands of things, we can't do that. And so we use machine learning models to get those quantities instead. And these models are built from thousands and thousands of DFT calculations that we all did with Psi4, and the properties are computed with Horton. Although now that we have MBIS inside, we can do all of this in Psi4 now, which is really great. The terms in red are obtained kind of in a more traditional way in terms of force field fitting, where we just fit to reference energies. And for these, we have all SAPT energies. This is SAPT2 plus paren3, delta MP2. This is what we call SAPT gold. It's pretty expensive, and so doing this for such a large number of dimers, almost 30,000, was quite an endeavor. But it's really amazing to have all that done. Again, all with Psi4. And so this sort of allows us to have to get this high level SAPT quality by fitting to such a high level of SAPT. Okay, so I'll just go to some results. First, looking at just a few small test sets. I'll start with the bottom here. So this shows IPML, which I mentioned is sort of the precursor to CLIF. And it's not designed to get accurate component energies, and so it doesn't do very well in getting these components, particularly for induction, where it fits basically to zero. I mean, to be fair, it's not designed to match these components exactly, but we still want the interpretive value of the SAPT components, and we see that by having this functional form that's very advanced in doing our fitting with respect to SAPT components, we get these SAPT components that match pretty well. And the question is then, well, how do the total energies look? Here's just a small table of tested on a subset of SSI. It's a neutral subset, comparing to some couple cluster reference data. And we see that for MAEs, RMSEs, our method does really quite well in comparison to sort of IPML, which also does quite good. Some other force fields, some empirical methods, and even SAPT0, we outperform a bit for this system. I mean, for this test set only, certainly not for everyone. But this was very encouraging. So it seems to be working pretty well. And we can apply Cliff just sort of to anything we want to, because the parameterization is automatic. We don't have to worry about any of that kind of stuff as long as the element types are within sort of the definitions of Cliff and everything's neutral, which is a pretty big limitation. But with all of that said, I mean, we can kind of apply it to whatever we want to. And so we did that. So I'll finish with just a little bit of this protein ligand system. What we wanted to do was compute these delta delta E's, which is basically saying if we have a ligand in a binding pocket, what's the difference in interaction energy if we change, say, the chlorine with a methyl? So if we're doing some sort of drug design, these kinds of quantities are very important. We looked at this with a number of different protein ligand systems here, and they're all fairly small. I mean, no bigger than about 200 atoms, so we do have some SAP0 reference values. And to be able to match SAP0, we have a version of Cliff called Cliff0 where we parameterize to SAP0. So the goal of this is to match this exactly, or as close as possible. And what we see for these values is that it does pretty good. The most important thing is to get the relative ordering of the ligands right. And it does that for all but one case where it does really quite poorly. And I don't really have an explanation for that. But, on the whole, I'd say it's pretty good. And then when we apply sort of normal Cliff, which is parameterized to high-level SAPs, we see it's not guaranteed to match SAP0 certainly, but something interesting highlighted in blue, where it gets different ordering for two ligands that we got right with Cliff0, which suggests that maybe SAP2 plus 3, so on and so forth, wouldn't agree with SAP0. But again, these systems are too large for the high-level SAP, so maybe this is, gives us a bit more insight here. And just for some completeness, I show the correlation we get between Cliff0 components with reference SAP0 for components and total energy. The red dots should be on the diagonal line, and they kind of are for the most part. The blue dots aren't guaranteed to be on these diagonal lines, and for dispersion, interestingly, it's much larger, which is maybe not surprising because SAP0 underestimates dispersion. For these systems is, I guess, the conclusion here, which is also can be linked to why maybe these ligands are different because dispersion is particularly important for the system. Yeah, and that's about all I have for this. I'm happy to answer any questions. I know I went through everything pretty quickly, but yeah, it's exciting work to be doing something so different that leverages so much of so many psi calculations.